There are two forms of the theory of relativity, the special and the general. Special is used in the sense of limited to special circumstances. It is, in most circumstances, only approximate, but becomes very nearly exact at great distances from gravitating matter. That came first. Einstein later developed the wider general theory, which can cope with gravitational matter. Whenever gravitation may be neglected, the special theory can be applied, and then the interval between two events can be calculated, when we know that distance in space and the distance in time between them, estimated by any observer. The special theory lets us describe one interval in space-time, that is, space-time, which replaces the two intervals in space and time of the older physics. Before dealing further with the special theory of relativity, I want to try to convey to the reader what is involved in the new phrase, space-time, because that is, from a philosophical and imaginative point of view, perhaps the most important of all the novelties that Einstein introduced. Suppose you wish to say where and when some event has occurred, say an explosion on an aircraft. You will have to mention four quantities, say the latitude and longitude, the height above the ground, and the time. According to the traditional view, the first three of these give the position in space, while the fourth gives the position in time. When people said that space had three dimensions, they meant just this, that three quantities were necessary in order to specify the position of a point in space, but that the method of assigning these quantities was wholly arbitrary. You could use any direction and origin for your measurement. But the only arbitrary elements in the reckoning of time were thought to be the unit and the point of time from which the reckoning started. One could reckon in hours, days, or years, in Greenwich time and New York time. Both these were trivial. There was thought to be nothing corresponding to the liberty of choice as to the method of fixing position in space. People regarded time and space as quite distinct. The theory of relativity has changed this. If one event is simultaneous with another in one reckoning, it will precede it in another and follow it in a third. Moreover, the space and time reckonings are no longer independent of each other. If you alter the way of reckoning position in space, you may also alter the time interval between the two events. If you alter the way of reckoning time, you may also alter the distance in space between two events. Space and time are no longer independent, any more than the three dimensions of space are. We still need four quantities to determine the position of an event, but we cannot, as before, divide off one of the four as quite independent of the other three. It is not quite true to say that there is no longer any distinction between time and space. As we have seen, there are time-like intervals and space-like intervals. But the distinction is of a different sort from that which was formerly assumed. There is no longer a universal time which can be applied without ambiguity to any part of the universe. There are only the various proper times of the various bodies in the universe, which agree approximately for two bodies which are not in rapid motion, but never agree exactly, except for two bodies which are at rest relatively to each other. The picture of the world which is required for this new state of affairs is as follows. Suppose an event, E, occurs to me, and simultaneously a flash of light goes out from me in all directions. Suppose I could observe a person in Sirius, and the Syrian could observe me. Anything which the Syrian does, and which I see before the event E occurs to me, is definitely before E. Anything the Syrian does after seeing the event E is definitely after E. But anything that the Syrian does before seeing the event E, which I see after the event E has happened, is not definitely before or after E. Since light takes years to travel from Sirius to the Earth, about 17 years in Sirius may be called contemporary with E. Dr. A. A. Rod suggested a point of view which helps understanding this state of affairs. He maintained that one event can only be said to be definitely before another if it can influence that other in some way. Influences spread from a center at varying rates. Newspapers exercise an influence emanating from London at an average rate of about 20 miles an hour, rather more on long distances. Anything a person does on account of reading a newspaper article is clearly subsequent to the printing of the newspaper. Sounds travel much faster, and radio signals travel with the velocity of light, so that nothing quicker can ever be hoped for. Now, what someone does in consequence of receiving a radio message is done after the message was sent. The meaning here is quite independent of convention as to the measurement of time. But anything that is done while the message is on its way cannot be influenced by the sending of the message, and cannot influence the sender until some little time after the sending of the message. That is to say, if two bodies are widely separated, neither can influence the other except after a certain lapse of time. What happens before that time has elapsed cannot affect the distant bodies. Suppose, for example, that some notable event happens on the sun. There is a period of 16 minutes on the Earth, during which no event on the Earth can have influenced or been influenced by the said notable event on the sun. This gives a substantial ground for regarding that period of 16 minutes on the Earth as neither before nor after the event on the sun. The paradoxes of the special theory of relativity are only paradoxes because we are unaccustomed to the point of view, and in the habit of taking things for granted when we have no right to do so. This is especially true as regards the measurement of length. In daily life, our way of measuring length is to apply a ruler or some other measure. At the moment when the ruler is applied, it is at rest relatively to the body which is being measured. Consequently, the length that we arrive at by measurement is the proper length. That is to say, the length as estimated by an observer who shares the motion of the body. We never, in ordinary life, have to tackle the problem of measuring a body which is in continual motion. And even if we did, the velocities of visible bodies on the Earth are so small relatively to the Earth that the anomalies dealt with by the theory of relativity do not appear. But in astronomy, or in the investigation of atomic structure, we are faced with problems which cannot be tackled in this way. We cannot make the sun stand still while we measure it. If we are to estimate its size, we must do so while it is in motion relatively to us. And similarly, if you want to estimate the size of an electron, you will have to do so while it is in rapid motion, because it never stands still for a moment. This is the sort of problem with which the theory of relativity is concerned. Measurement with a ruler, when it is possible, gives always the same result, because it gives the proper length of the body. But when this method is not possible, we find that curious things happen, particularly if the body to be measured is moving very fast relatively to the observer. When two bodies are moving relatively to each other, lengths on either appear shorter to the other than to themselves. This is the Lorentz contraction, which was first invented to account for the result of the Michelson-Morley experiment, but which now emerges naturally from the fact that the two observers do not make the same judgment of simultaneity. The way in which simultaneity comes in is this. We say that 2 points on a body are a meter apart, when we can simultaneously apply one end of a meter rule to the one and the other end to the other. If now two people disagree about simultaneity and the body is in motion, they will obviously get different results from their measurements. Thus, the trouble about time is at the bottom of the trouble about distance. If the body is moving very much more slowly than light, the alterations produced by the motion are very small. But if the body is moving nearly as fast as light, the effects become very great. The apparent increase of mass in swiftly moving particles had been observed, and the right formula had been found before the invention of the special theory of relativity. Lorentz had arrived at the formulae called the Lorentz transformation, which embodied the whole mathematical essence of the special theory of relativity. But it was Einstein who showed that the whole thing was what we ought to have expected, not a set of makeshift devices to account for surprising experimental results. Let's review the reasons which have made it necessary to substitute space-time for space and time. The old separation of space and time rested upon the belief that there was no ambiguity in saying that two events in distant places happened at the same time. Consequently, it was thought that we could describe the topography of the universe at a given instant in purely spatial terms. But now that simultaneity has become relative to a particular observer, this is no longer possible. What is, for one observer, a description of the state of the world at a given instant, is, for another observer, a series of events at various different times, whose relations are not merely spatial, but also temporal. We are concerned with events rather than with bodies. In the old theory, it was possible to consider a number of bodies all at the same instant, and since the time was the same for all of them, it could be ignored. But now we cannot do that if we are to obtain an objective account of physical occurrences. We must mention the time at which a body is to be considered, and thus we arrive at an event. When we know the time and place of an event in one observer's system of reckoning, we can calculate its time and place according to another observer. But we must know the time as well as the place, because we can no longer ask what is its place for the new observer at the same time as the old observer. There is no such thing as the same time for different observers unless they are at rest relative to each other. We need 4 measurements to fix the position, and 4 measurements fix the position of an event in space-time, not merely of a body in space. 3 measurements are not enough to fix any position. That is the essence of what is meant by the substitution of space-time for space and time.